Hello and welcome to Rudy's Electronics Labs. Last week I came across a device that I got very intrigued by. It's standing right over here in my lab now, and it's the Rohde and Schwarz ZPU vector voltmeter. And I was really wondering, what is this device really about and what were the type of things were people using it for, and would it still work here? And to understand a little bit what this unit is, because I dug a little bit into its history, and I was also lucky to have the full documentation with the device, the service history, the full schematics and user manual. Well, to know what this device is all about, well, nowadays we can do a lot of fancy measurements with vector network analyzers, spectrum analyzers, with oscilloscope with high frequency, all allowing us to work in the high frequency domain. But let me now take you back 50 years in time. I'm going to the year 1974. And at that time I was still a little kid, but my father, who was also an engineer, was already introducing a bit into the world of measurement, and actually at that time I was making measurement together with him with this Metra test multimeter here. But this one obviously only allows you to measure some voltages and currents. We took good care of it, even though it has a little bumps, it has seen a little bit more current that it should have those back in those days. But if you really wanted to measure very small voltages and go into the domain of high frequencies, there were much more advanced devices that actually allowed people to do all the type of HF measurement that they needed to do those days. And that is basically what the ZPU is about. So in this video I want to introduce you to the device and the way that it works. But we're also going to be doing a little bit of testing ourselves and seeing what still works well with the unit that I got right over here. And we will also see that this unit actually has some rather sophisticated equipment in it, and actually even in a place where I least expected that to be the place. But I'll get to that in a moment. Now, first of all, the basic type of characteristics. It's a device that measures voltages and phase. Now, voltages, it can measure quite small amount of voltages. It allows you to measure less than 3 microvolts up to 1 volt, and with a divider up to 100 volt. It was originally with the unit, but I don't have that divider. We can measure those things all the way up to 1 gigahertz, and the measurement error is relatively small at 2%. At least that depends on the frequency range that you're measuring in. And given that we got 2 beautiful analog meters here, yeah, that's probably not getting any closer. And we can also do some ratio type of measurement between channels. I get to that when I do my measurement test here. And you can do phase testing. You got a phase tester, that's the other analog meter that we got right over here. It can measure, show phases basically from minus 180 to plus 180 degrees, but you can also let the meter just show you minus 6 up to plus 6 degrees for small phase differences. And according to specifications, we could measure phase all the way to a resolution of 0.1%. So that's already quite impressive, I think, in terms of specs. But really, what were people doing with this? Measuring voltages and phase, what the type of use cases? And in the user manual and in a couple of brochures and in an article that was in the Rohde and Schwarz magazine, etc., we got a number of different use cases that are being shown, including the setup and the whole way you will be carrying it out. And so what are these type of use cases here? Well, you could use this device to compare the frequency of 2 signals, for example, to frequency references, but also very precise crystals or so. Secondly, you could determine the characteristics of amplifiers or filters or modules or whatever, so you could be kind of characterizing their gain, their phase shift, and their group delay. And you can even make, if you add some other equipment together with it, you can even make some nice graphs out of that, so we actually see the exact behavior of amplitude and of phase over frequency, huh? A bit the way that we would do with modern vector network analyzers. You could actually measure antenna radiation patterns, and you see some great pictures of that in the user manual, modulation depth measurements, You can even measure like S parameters and measure something like the electrical length of cables. But in order to do that, you will need also to have one or more directional couplers together with the device to do that type of measurements here. So you see, we're already getting into the domain of quite advanced type of measurements and characterization of equipment. Now, and how does it do this? I'll show you in a moment a couple of pictures, actually quite full of equipment here. And let me just highlight some unique features. So what we're having actually is a two-channel tracking receiver. So we got two fully identical channels here that both go to 1 gigahertz, and the first channel is a tracking receiver which supports auto-tuning. So it synchronizes itself automatically to the incoming signal between 100 kilohertz and 1 gigahertz, but you have to set the range in 10 steps, in decade steps, where it has to look for that signal. It does not have to be a constant signal, it also allows signal sweeps up to 30 megahertz a second. And this is going to be very useful if you want to do automatic characterizations where you are kind of playing with sweeping the frequency and you want to see the phase response or the amplitude response as a function of that. And then having shown on a recording device or an XY oscilloscope or any device like that. Now, in order to do these type of tricks, it actually has an incoming signal and it down converts it, but all the way to 20 kilohertz using a sampling stage, a sampling type of mixer there. It got outputs on the back for all types of stuff, like outputs of the IF signals, but it also got the outputs of the measurements, like the voltage and the phase measurements, again, to be able to use a external recorder with a tape and paper, or using a oscilloscope or oscillograph or that type of stuff. That's how it was called, oscillograph, they call it in the manual of the device. There are also a lot of very cool accessories that exist with the unit that I unfortunately don't have, and I'm particularly missing some of the accessories to connect the measurement probes that I got right over here, to BNC, to have an insertion unit for the measurement probes that you can insert them in an existing cable or circuit or so, and the 50 ohm terminators and a couple of more things. I think they're extremely hard to get by. I saw some being offered, but at really high prices. Oh, and one last thing that the unit also supports, mind you, it's remote control. So setting, for example, the frequency range or setting the voltage measurement parameters, etc., can all be done remotely. It's not a very common interface. You have to look a little bit how you program it with a large number of pins and putting signals on them. But it allows basically remote control of many of the functions, like whether you're looking at channel A, B, or ratio A, B. All that stuff can be remotely controlled. Now here you see the block schematics of the device. I don't want to go into many details here, but basically we're seeing back here that we got two completely independent channels here, identical channels that are measuring. Actually, there's one significant difference between the channels still. The first channel cannot accept as small voltages as the second channel. This is a design choice in the device because the first channel also has to be used for synchronization with the auto-tuner here. And that is the reason, according to the manual, it got a different measurement range. But otherwise, we got two fully identical channels, and we basically need that if we want to compare characteristics, for example, between the input and the output of a DOT and characterize the device here. And all the way in the beginning, I don't want to go through the whole schematics here, but we see the sampling stage here. And this is where the really interesting things are kind of happening. And as I explained in the manual of the device, what we're actually doing is we'll take a high frequency signal and then we go sample it using an impulse generator, which is creating very fast small impulses, and every time it is basically sampling the input signal and doing that by something that is multitude lower than the incoming frequency. We basically can create an IF signal that respects the original amplitude, the waveform, the phase differences and the harmonics of the original incoming signal. And that sampling is taking place by a switching diode, which is basically sampling different values and storing the current value in a capacitor. So we're not digitizing, huh? Often we these days talk about sampling and then digitizing, but here we're basically talking only of the sampling or sampling and hold, if you wish to call it so. So the interesting stuff, I think, really is where exactly is that sampling taking place. And now, I told you I have all the schematics. Well, that's almost true. I think I got like 30 or 40 pages with schematics and PCB layouts. And here we get to see the schematics of the, what they call, I think, the post amplifier. So we see the signal coming here from the measurement heads here. So the testkopf, as it's called, we see them coming in on the left. And on the right of the schematics, we also see some signals that actually send back to the measurement head here. So there's some bias signal there. There are actually also impulse signals going there. But the actual sampling, so the switching diode, etc., are not part of the circuit I'm seeing right here. And if I look at the at some more of the schematics of the device on the right hand of your screen, you also see again the same post amplifier that I was just looking at. But then you see actually four they are small. We see four isolated wires going into the measurement probe. And that is apparently the signal coming from the probe and the signal going back like bias and impulse type of signals. But the real magic seems to be happening within the probes themselves, in the testkopf probe. And that is the only part of the schematics basically that we don't find in the manual of the device. We don't see the precise way these things work here. But later I'll dissect the device a little bit more and we get to learn a little bit more about the actual way that the sampling head is working. A bit of information I found there is that the two scanning stages consist of equal thin film circuits incorporated in the ZPU probes, each of them comprised of a gate of 4 diodes arranged in a bridge, a storage capacitor and a FET amplifier stage. And then it goes to a post amplifier and some other things are happening there. But this is basically the part where the signal is being captured, brought to a 20 kilohertz signal, and then it's much easier basically to deal with, and we're going to do all the measurement that the device supports here. Investigating now further the probes, they're connected to the unit here by this module, and actually this whole module can come outside. So the whole RF part is maintained here in a module, and it actually goes into the back and also interfaces with the unit and even to the outside world. But the probes themselves are fixed entirely to this unit. So it's an interesting question why exactly they did that, and we're going to find out a little bit more about it. Here I'm getting the 2 probes here. Okay, so let's take a closer look at this probe now, and we can actually turn it around here, the tip. This is also described in the user manual. The little tip turns as well, and what happens here, it comes apart. We see here, and if we look very carefully, we see here the probe tip with 4 different wires here, and here a connector with 4 different holes and a centering tip, and there is a little red line. The first time I took this apart, I was really shocked because to put it back, you must align that with another red dot here, and I couldn't find the other red dot. No ID, and since this whole field turns also, you can't find out about the absolute orientation. However, it works slightly differently, I found out later. If we now take here a tool, we very carefully pick it out. Look at this. This is the actual active probe tip. This is where the electronics are that are doing the sampling of the input signal and the down conversion right away to 20 kilohertz. So let's put this particular part under the microscope and inspect it in a little bit more detail. Now here we got the measurement probe or the insights under a microscope. And just on the right hand side you can still see the 4 connectors that actually are connected via the measurement lead basically to the device itself. And so we see a number of small components here, and completely on the left hand we see the part basically where the tip of the measurement probe is pushed into, I think, with a small spring or so. Now, as you might remember, we should be We found in the text somewhere that we should find 4 diodes here. We should also find I think the switching diode. There should also be a FET preamplifier, a capacitor that stores basically the sample and whole value. So these are kind of components I must admit that I'm not very familiar with. I never try to work with them, but let's make it a little bit bigger under the microscope. And this is probably what I think to be the 4 diodes here. And we got some other components here. One of them probably being the FET preamplifier device, and one of the other the switching diode. Even though one of them, the 2 wire terminals are connected to the same part here. So I don't know exactly what is, but it's quite exciting to see this like very, very fine type of electronics all the way hidden in a place where I least expected it, really part of this tiny, non-assuming looking measurement probe. Now let's try and go measure something with the vector voltmeter. So I got a little setup here, and it's basically just a signal generator here, which is creating 2 10 megahertz signals, and I'm bringing to this device. Unfortunately, because I don't have the right adapting probes for 50 ohms BNC inputs, I have to walk a little bit with it, but I think it's going to be okay for this type of frequency range for this testing. Okay, so let's go and see and offer a signal to the device. So I'm turning on here the signal generator with 500 millivolts amplitude, and since the device is not a 50 ohm device, I don't need to correct for 50 ohms, and we see nothing happening yet in terms of incoming voltage. But that is not strange, because it's a device that should tune into the incoming signal, and we have to choose the right range. So if we go up here, now basically we see that the little light went off. It's basically telling us that it is synced. I would have preferred to see the other way around, I guess, with light. Initially, I thought that Rohde and Schwarz made this button a little bit sloppy because it's between these measurement values, but actually it's just right here. This is indicating the range, which is roughly between 10 and 20 megahertz, and there's actually a table where you can see what the range are conformed to. They're overlapping to some degree, which is nice. So now our receiver is actually locked, the light went off, so the red light basically says looking for sync, and not so much I am in sync, because now it's off and he is in sync. And I read the value on the meter here. Then I want to try the second channel as well, so I'm going to channel B here, and I create exactly the same signal, and I'm turning it on here, and we're getting it on signal B. Now, since this is a voltmeter, we want to measure how much we got here. We are on the range of 0.3 volt per full scale. So relating here to the 30 that we see over here. So we're reading like 120 millivolts or so. But what exactly is that? Because I'm sending here 500 millivolts pp. Should we be looking at RMS? Should we be looking at something else? I didn't see exactly that relationship. I also checked whether nobody had been playing around with this button here and screwed it back wrongly, but I could also confirm that this button is properly into position. So I decided to measure stuff a little bit from the oscilloscope and trying to see what type of measurements that we're getting here. So here we're getting the oscilloscope screen. This is the incoming waveform into the device. What I'm seeing is not 500 millivolts, it's 420 millivolts. I think that is because of the input load of the device. It's not 50 ohms. It should be rather high, I think 100 kilo ohm. So it drops a little bit more than I would have expected it to drop, but you know, I'm not too concerned about it. Let's just face the fact that this is 400 millivolts. RMS volt is too high too for what we're measuring. The amplitude's also too high. So I've been thinking about this a little bit, reading the manual. I didn't find any convincing explanation there. And after thinking a little bit more, I think I got what it actually is. I think the voltmeter is actually just looking at the positive part only, the upper part only of the sine waves, and taking that average. And so to see what that value is, we can basically create that signal here with the math function. I already created it here. This is just the absolute value here. And I also created a measurement value here that can show us what it is. So I'm activating it here, measurement number 4. There we go. So we're seeing here that out of this absolute signal here, only the positive part, the mean value is 120. And so that, I think, could be pretty much what we're actually reading on the device itself here. So that's, I think, the voltage level that the device is reading. Now, one more thing that the device can do in terms of voltage measurement that I want to mention, that it can compare the two incoming voltages here. So what you basically would do is that you would connect both of the channels to the same source and calibrate them, set the ratio to 0 dB on the dB scale, and then you can look at differences. Now let's go and do that. I'm just taking the signal as they come in. I'm going to use here this manual indicator to put it on 0 dBs. I'm not writing from the screen. There's a nice mirror here. But basically, if I go to channel 2 here on my signal generator, and I would start to play around with the amplitude here, I could see the amplitude of channel B relative to channel A in dBs. So this is very nice, basically, to characterize devices. This is already one step into characterizing amplifiers and all types of things, etc. Just remember, this is of course dB in relation to voltage, not dB in relation to power, which of course follows other laws. Now the next step, of course, what we're interested is in the phase part here. That's arguably the most interesting part of the device. So let's go and check that out. And I'm sending 2 signals in here still of exactly the same frequency and without any phase difference. It's actually exactly the same signal coming out. I can also use tracking, but I double checked it. It's the same signal here. And here we should be seeing the phase relation. And we can see that on a scale of minus 180 to plus 180 degrees, but we can also zoom in on phase difference. I will do that in a moment. But let me just start by introducing a phase difference here in channel 2. And let me just let it go to 120 degrees of phase difference compared to the other channel. And there we go, 120 degrees. So without any problem, we can measure here the phase differences between the channels, minus 100, wherever we want to go, picking up this phase signal here. And we can also look at fairly small differences. And there I also want to demonstrate the adjust function here. So what I'm going to do here, to do that, I'm going to go to a positive phase of 50. And now I want to try to measure a phase difference relative to the 50. So I would start to calibrate that. And there's actually a calibration possibility here in like 10 degree steps. So let me try to put this more or less at, so that should be about 5 steps, because I'm looking at 50 degrees. And now I'm going to go a more sensitive scale, plus minus 60, plus minus 18, and I can use this little adjustment over here. And I can even go to just 6 degrees. It's going to be super, super sensitive here. But I'm going to give it a go. Let me see if I manage to keep it. Yeah, so I think I got it more or less on the scale. So we're now looking at only 6 degrees plus and minus. So if I add 5 degrees of phase, so from 50 to 55 degrees of phase, yeah, it goes all the way here to 5. So it's super sensitive, and according to the original specifications, this device could measure phase differences as small as 0.1 degrees. Now, the device is a bit old and probably not properly calibrated anymore, but I hope this gives you a little bit of idea of the possibilities, and kind of amazing that you were able to do this type of measurement 50 years ago. Now, another thing that we will be able to use the device for basically is look at differences between frequencies and a frequency reference, for example. So let's quickly go into that. We're back at 180 phase screen here. And instead of just introducing a phase difference, I'm just going to introduce a different frequency. And I got 10 megahertz, and I'm just adding 1 single hertz to the 10 megahertz. So that's 1/10 of a million of difference here. And what happens here? Yeah, every second we see basically the meter going the extremes, more or less. So this is exactly what we should be expecting to see, because it's one frequency off, so every second it goes through that cycle, and if we go faster, then it would go twice a second or so, making this type of movement. So this really allows us to calibrate or test two sources where they have exactly the same type of, the same frequency here. Now the device can also output several types of signals, both the IF signals basically, as well as the measurement output. So let's take a quicker look at that as well, and also how those outputs I've connected to the oscilloscope over here. I'm going to move again here to the oscilloscope, and what we see right now is in yellow and in green we see the IF signals of the device. So let's quickly investigate one of them. I'm going to tick channel 1 here. Oh, I just turned it off, and I'm going to do some quick measurements on it. And what do we see here? Channel 1 is basically a channel of exactly 20 kilohertz. And that's true, that's the IF frequency. So it down converts both of these signals basically into an IF frequency of 20 kilohertz, and then it starts comparing these. So if I show both of them at the same time, I do know there's a little phase difference. I mean, the device itself is not showing a phase difference right now, but the outputs are. So I wonder if something got slightly drifted in the outputs, because I would expect them to be together. It's a difference of some 20, 30 degrees I measured before, and I'm not sure that is quite correct here. And you see one other line here, which is the orange line on channel 3 of the oscilloscope, and that is actually connected to the measurement output, to the phase output, and that is basically a voltage representing the measurement output. So now if I would again do a small difference in the frequency between the two channels, what we basically see now moving up and down is, well, of course, it's basically the meter that we see jumping over here, and that we see in the form of a signal. And this you could also basically send to an oscilloscope. You might want to use XY mode, you might use a sweep device as a frequency generator, and then the output, basically the vertical scale, might be this one, and you could directly make XY plots basically of frequency behavior and amplitude and phase behavior as a result of frequency. So that's kind of super cool what this device allows you to do. Okay, I thought I owed you one more analysis where we really see some of the more advanced measuring type of setups we can do with the device over here. So what I'm doing here is that I'm taking a little circuit over here. It's a mini circuit. It's a bandpass filter from 175 to 237, and I'm going to try to capture at least a part of that bandpass characteristics, both in amplitude and phase. And so what I took is a SMIC SMIQ signal generator, and that one has a sweeping function, and a nice thing is that parallel with the sweeping function you get a voltage out that represents where we are in the sweep. We're going to measure that over here with the new device, the vector voltmeter, ZPU, and the final result I'm sending here to this vintage Tektronix 2465A oscilloscope. And I like the XY mode here, and also nice about the XY mode that we can have several channels active, so I see two little dots here. And right now I'm sweeping slowly between the frequencies of, and let me get down in the menu again here, between 200 and 210 kilohertz. And I'll tell you in a moment why I'm doing that right now. And so what I'm seeing here is this dot going from the left to the right, and see my meters moving here, and sometimes slowly moving, but also moving a little bit erratically. So what is going on with this test setup? I was originally hoping that I could create a nice, very smooth picture here on this oscilloscope. And why was I hoping that? Because the specification of the ZPU tell us that it's able to deal and to auto-tune with sweeps as fast as 30 megahertz per second or so. So what is actually happening here? I've been trying a number of different things in this setup here, but I have a lot of trouble when I when I activate sweeps, basically that the device stays stable. Once in a while, it kind of, and quite regularly, it kind of loses sync, the auto tuner. And then we see everything flashing up and by. And if you would wait long enough, you actually see, you know, the whole pattern being nicely generated here on the device, if we would just ignore this, yeah, erratic jumping going up and down here. So it's kind of doing what it's supposed to be doing, and you would see slowly here the amplitude, which is actually the incoming, the ratio between the outgoing and the incoming amplitude of my filter here, and the phase. We see just that the phase shifted all the way to the other side because we just went to another sweep again. So we also see the sweep, the phase moving gradually down, but we're really suffering from all this type of erratic behaviors because the tuner can't keep up. Now let's investigate that a little bit deeper. And to investigate that a little deeper, I'm going to get my oscilloscope out and I'm going to examine the XY plot in a little bit more precise manner. Okay, now we added the Rohde and Schwarz to the setup, and we just have it showing the same thing as over here, but one of the things is that we can actually use infinity type of mode in which we're able to track our signal much better. So what we see going on here, well, we see the different waveforms and we also see the combined, or the XY plot over here. I really like the way that you can use two channels for XY. We can slowly see here the time, so the X to the Y building up, so that we're going left to right here. And actually this is the only modern oscilloscope that I have that can show two channels in a XY plot. All my other ones can only plot one, and my very old one over there. I think that can even do 4 at the same time. Okay, so what do we get to see here? It's promising but also concerning a little bit, because we see here, and actually we're right now somewhere over here, we can see on the positive side that we actually see two curves, in which the green one is the amplitude curve and the orange one basically is the phase curve, are being plotted well, but we do again see these disturbances. And what we also note that these disturbances come at a very regular rate, and that is peculiar or so. So it's not that our tuner is randomly kind of getting out of tune or so, but it's actually at very precise moments in time. Hey, we see our phase shift going on, by the way. I mean, that all works very well, but everything is messed up more or less by these disturbances we got here in the signal. So we need to find out in more detail what the disturbances are coming from. And I now really start to wonder, is this something that this tuner is not working properly, or should I further investigate the SMIQ signal that's coming out of there? So probably my easiest thing to measure anyway. Let's first see if the SMIQ is actually as smooth as I thought it would be. Now connected the signal SDS oscilloscope here to investigate the signal of my SMIQ, and it's still running exactly the way that I left it with the previous measurement. And I'm starting up the scope and I'm seeing a rather dirty signal. So what is going on there? Actually the SMIC is not creating this dirty signal, but it's actually coming from the measuring probes of the vector voltmeter. So this impulse type of measurement that is doing actually does reflect back into the source. This is quite relevant to know. So this measurement instrument has a bit more impact on your DOT or your measurement source as you might believe it be. So let's disconnect it from there and just look purely at the SMIQ output signal. So we got it here. Okay, that is a clean signal, and that looks nice. And did you see that? And another one. Let's be patient. Yeah, and another one. So really, I didn't know that. But the SMIQ is actually, when it's sweeping, it's not a nice smooth sweep. And there's a moment, I think, where it kind of gets out of sync and the the new bandwidth, it's the new frequency sending out. It kind of doesn't start at the same phase point as the other one. I mean, I probably could go more time into investigating this, but really I have to conclude that the problem in my measurement setup were not so much that the auto-tuner here didn't work well. This I don't know yet, but for sure I know that the SMIQ has issues sending out a smooth sweep frequency signal. Yeah, we see it all the time coming back, and also at very regular type of intervals. So maybe this is when it's moving between ranges or whatever, but it's at very regular intervals. Actually, the reason why I started doubt it is that the intervals were too regular for me, and so I really started to suspect this digital device creating it rather than this device getting out of tune. That would be a bit more erratic, I would say. So yeah, I learned something interesting, both from the SMIQ in terms of non-smooth sweeps, but also in terms of the ZPU, that it actually reflects back these measurement probes reflect back some stuff into the device in question, which actually include a DC component here as well. So it's something to be aware of. Okay, I'm giving this one more go, and now actually using the signal generators instead of the SMIQ. And the reason I got both here, because you need to do a little trick in order to make a sweeping signal and a constant voltage signal representing the sweep. I'll post a separate tutorial on that. But we see here that the signal that it has generated basically on the oscilloscope here, we see the frequency growing slowly, and we see the DC signal getting up here. So let's see how our vector voltmeter is dealing with it. So we can see he gets a signal, he's tracked on it. We see slowly the meters moving, and we can actually see here also on the oscilloscope right here with the X and Y plot, basically the dots going and slightly moving. Now let's see what the Rohde and Schwarz is doing if we try to plot here our signal, and we see the voltage ratio plot and we see the phase plot, and even though we get some occasional glitches, yeah, this is really showing what the device originally was designed to do, to be able to track down a relationship between, over time. I hope you enjoyed this video. This gave you kind of an idea how people were able to do advanced measurements back in 1974. Yeah, that's what it is. Thanks for watching.